Okay, welcome everyone to today's algebraic graph theory seminar. Today we have Nathan Lindsey from CU Boulder speaking, and he will be talking about complexity measures on the symmetric group and beyond.
Thanks for the introduction, Sophia. So yeah, this is joint work with Netta Daphne, Yuval Filmus, Noam Lifshitz, and Mark Vignoles. And so these are all theoretical computer scientists that are over in Israel. So yeah, so today's talk is going to be more of it's a computer science talk, but I've distilled what I think are kind of the things about the paper that would be of interest to people in our algebraic graph theory community. So I thought maybe let's start off with the sensitivity theorem. So I think we've had a lot of talks about this. So I know Max gave a nice talk in our seminar about this result, and so did Eric Morehouse in another seminar. But yeah, I won't go through the proof of this again, but I just wanted to remind us of this. So yeah, so this was this theorem had an amazing proof by Huang that they used a lot of tools that we know from algebraic graph theory, and through some known results of Godsmal and lineal, this also implied the following theorem. And this is what's called Huang's sensitivity theorem. And our seminars have spent we've mostly focused on this induced subgraph result, but the folks in the theoretical CS community really liked the corollary of Huang's sensitivity theorem, which told us something about this complexity measure called sensitivity in relation to the degree of the Boolean function f. So today's talk is going to focus, so hopefully by the end of today's talk, I'm hoping that the algebraic graph theorists among us are going to have a better appreciation for like why the computer scientists like this corollary to Huang's result. So yeah, let that be a goal for this talk. So I hope we'll be able to appreciate this result some more, the corollary that we have here. Okay, so here's just a brief outline of the talk. So I'm going to start by just defining complexity measures on the hypercube. So the hypercube, we're going to call this, sometimes I'll call this the Boolean cube. And yeah, so in the second part, we're going to generalize some of these complexity measures on the hypercube beyond the hypercube. So let's say some more interesting domains besides the Boolean cube. And then if we have time, I'm going to give just a quick application of some of these techniques to classifying degree 1 Boolean functions over over the domain of perfect matchings. So we'll see how some of these techniques where we go beyond the hypercube can help us say something about the structure of Boolean functions over perfect matchings. So you can think of this last result as being kind of an extremal combinatorial result where we are classifying characteristic functions of perfect matchings that have low degree. Okay, so I'm going to start with some review here. So this is just kind of complexity theory 101. So every function on the Boolean cube, so we can write the Boolean cube this way. In fact, computer scientists like to do this. So having -1, 1 to the n rather than 0, 1 to the n. But regardless of how we decide to represent the domain, we can write these functions in their Fourier basis. And so these chi-s's are characters, and famously these characters are indexed by subsets of a n element set. So I'm using this bracket n notation for an n element set. Right, so and there's a definition for the characters in case we've forgotten that. So, right, this is the bread and butter of theoretical CS as far as the analysis of Boolean functions goes. And there's an equivalent way that folks in computer science like to write these functions, and that is as a multilinear polynomial. So I can decide to change this to a polynomial notation where these characters are now these monomials. So so the character chi-s, we replace this with the monomial where my indeterminates are drawn from S. So yeah. And so I should say that these f hats, these are often called the Fourier coefficients. And so, yeah, so we can write a function uniquely as in this way on the Boolean cube. So the first complexity measure that I'm going to introduce, formally introduce, is degree. And so degree, we're just looking at a function on the hypercube, and we're just looking at its largest, or we're looking at the non-trivial Fourier coefficients, and we're finding the largest one that's not 0. And that's what we call the degree. So just a quick sanity check. So constant functions have degree 0. The parity function has degree n, so that's kind of the most complex, and linear functions will have the degree 1. So more generally, there's this notion of a K junta. So a junta is like, so there's kind of a colorful metaphor to describe these, but perhaps you'll understand why it's called a junta if we just carry on and read the definition. So it's a Boolean function f that depends on at most k coordinates. So this means that when I look at so I have n coordinates, and if I want to completely express the function, the Boolean function f, I just need to consider a subset of the coordinates. So in other words, I can find some function on a smaller hypercube, so like a k hypercube, and so if I know, so the function is determined completely by these k coordinates, I1 through ik. And a junta is like it's a generalization of a dictatorship where we have where it's determined by a few individuals. And so sometimes when k equals 1, the folks in computer science will call this a dictator. Okay. So there's an equivalent definition of degree now. So I've given us 3 definitions of degree. So and these are all equivalent, and this is actually something that's going to be important later on. So so we say that a degree f function on the n hypercube has degree k if I can write it as a real linear combination of k juntas. So this is kind of the picture that I want us to keep in mind. So when we're thinking about Boolean functions on the hypercube, so we have we can grade this. We can think of this as a vector space that's graded by Fourier level. So where I have Fourier level 1, which is indexed by these monomials of degree 1 or characters of degree 1. And then level 2, ... And these degree k functions we like to think of these as being kind of low complexity functions, and where k is something that is, could be constant, could be little o of n, is just something that's not scaling with n. Okay, so later we're going to generalize this picture to other domains besides the hypercube. Okay, so let's introduce another complexity measure. So decision tree complexity. So it's easy to see that the big part of computer science is understanding and analyzing decision problems. And so these decision problems are just nothing more than Boolean functions. And so if I wanted to decide the language that is 1 if x1 is less than x2, that it's less than x3, then this decision tree below is as an algorithm that will decide this. So I'll let you verify that this is indeed a decision tree for this problem. All right. And so the decision tree complexity is just going to be, it's the least possible depth of any decision tree T that computes this function f. Okay. So this complexity measure is a bit more combinatorial or algorithmic. The degree complexity measure is spectral. All right. So there's so one of the nice things in this area is that you know, we have many different ways of understanding or measuring complexity of these Boolean functions that on the surface seem like they might not be related, but in fact, we'll show that they have this so-called polynomial, they're polynomially related. Okay, so here's a more algorithmic measure of complexity. All right, and so just to formally show that how these complexity measures are related. So it's not hard to show that if I have a Boolean function and the decision tree complexity of that Boolean function f is k, then the Fourier degree has to be less than or equal to k. And so the way to see this is just by noticing that paths in this tree partition my hypercube into disjoint sub-hypercubes. So for instance, if I looked at this path where I query x1, and if it's a 0, then I query x3. And if that's a 0, then I query x2. And then if all of those are 0, I assign the value 1. So I have a sub-hypercube there on all inputs that are where I have x1, x3, and x2 is 0. And so what we can do is write f as just a disjoint sum of these paths, where f of p, so in this example, f of p would be 1 for this blue path that I have here. And this one, this one c sub p, this is just the characteristic function of the subcube induced by that path. So yeah, and the important thing to notice here is that this one c sub p, like this characteristic function that I have here, this is a junta, so a 3 junta in this case. I only need to look at 3 coordinates to write down what it is. And so it's a linear combination of juntas. So I have that degree, the degree can't be greater than k. So the hard direction is showing that, and this was done by Nisan and Szegedi in '94. So if I have if my Fourier degree is k, then I can find a decision tree actually that is not too large. So polynomial in k. And they were also able to show, I believe, that the decision tree that we get from so if the degree is k, then my decision tree, it has to be super linear in k. So it has to be super linear, but it's still polynomial. And so this is I think this is a surprising result when you look at it from fresh eyes, because what this is saying is that like this spectral condition that we have on degree, this translates into a algorithmic, an algorithmic notion of complexity. So we can actually find an algorithm, a very naive algorithm that will compute us, like that will actually compute this function. So this is saying that these decision problems that have low spectral complexity also have, in some sense, like low algorithmic complexity, which is very cool, I think. Okay, and so in this situation, we say that these two are polynomially related. Okay, and so this is kind of the, I mean, there's tons and tons of these different complexity measures that are very natural to consider in other contexts in theoretical CS. And so I won't go through all these, but one, like the common theme in this area of complexity measures of Boolean functions is that like all these different notions of complexity that we come up with for studying Boolean functions, they all seem to be they're all polynomially related. And so this is in theoretical CS, this notion of being polynomially related is very familiar. So it's kind of it's a very natural equivalence class. Okay, so just to give you a taste of like how well studied this area is and how many different complexity measures there are for these Boolean functions, I'll let you visit this website. And so it kind of has an up-to-date table of all these relations between various complexity measures. And so what was, so the reason why the theoretical CS community was really pleased with this sensitivity result was due to the fact that like sensitivity wasn't known to be polynomially related to any of these complexity measures until last year. So let's define what sensitivity is, even though we've got a taste of it on the first slide. So, so the local sensitivity is of a function f is on an input x is we're just counting the number of influential coordinates. So these are indices I, where if I flip the ith bit and I look at the difference between the function on x and the function where on x where I flip the ith bit, the function value changes from a 0 to a 1 or vice versa. So we're counting the number of indices that are influential, and the sensitivity of f, we're just taking the max over all local overall inputs. So this is so this complexity measure, you can think of this as being like a discrete analog of smoothness of that measure for continuous functions. And I've even written it in I've written local sensitivity in such a way that suggests that maybe this is, maybe there's some way to couch this in terms of, say, like a Lipschitz constant or something like that. And if you work with it and think of the hypercube as a discrete metric space, then you can derive an inequality where you get something where the sensitivity S of f sort of looks like a Lipschitz constant in this inequality, but I won't go down that path. But suffice it to say that this sensitivity, this is sort of like an analytical, discrete analytical measure of complexity. So we've seen degree, which was spectral. We've seen decision tree complexity, which is like combinatorial or algorithmic. And we've seen sensitivity now, and this is like an analytic one. And so Huang's sensitivity theorem states that that the sensitivity is at least the square root of the degree of the function. So so we're relating now an analytical property with the spectral property. And so one way to, like I guess a nice way to sum this up is saying that smooth functions are easy to compute. So I can in particular, this result shows that sensitivity is polynomially related to these other complexity measures. So I can find a somewhat shallow decision tree that computes a smooth function. And again, I think that's very neat. Okay, so theoretical computer science has been certainly blossoming over the past, I don't know how long it's been around, maybe at least since the 60s. But I guess, but anyways, it's what I'm trying to say here is that theoretical CS has gotten past its hypercube roots and is now looking at other domains besides the hypercube. So these these 6 items that we have here. So when I say scheme here, I'm referring to an association scheme. And so this is just kind of, I think most of the folks in this crowd are familiar with association schemes. So, so recently, so this is by no means an exhaustive list, but over just the past 2 years, if you just look back 2 years, you can see results. So these results are from from the theoretical CS literature, and they're drawing from the Johnson. They're using the Johnson scheme, the Grassman scheme, the bilinear form scheme. So there's just been a lot of interest in the theoretical CS community to move beyond the hypercube, but yet continue to do sort of these Fourier analytical Boolean function type arguments. So yeah, I won't go into the details of everything that's in these references. If you want to know more about these references, you can cross-reference it with the archive paper. But anyways, don't want to belabor that point too much. But these recent works in theoretical CS that involved some of these association schemes that we're familiar with, it certainly motivates the following question. So like, what's the right framework for taking all these complexity measures of Boolean functions to other domains? So we have this, so the theoretical computer scientists have developed this nice toolkit for understanding Boolean functions on the hypercube. How can we take this out of the hypercube? So, so here's just, you know, a bunch of combinatorial domains, and you can ask yourself, okay, well, is there like a common framework that where I can capture all of these domains and still recover and still have well-defined notions of complexity measures? So one of the main contributions of this work is that we're able to give like a framework that's somewhat based on abstract simplicial complices to capture many of these combinatorial structures. So I'll talk a little bit about this framework, but so there's a lot of parameters. I think the most important ones are, so we have this notion of a universe, a domain, and a query. So, okay, so we have a set U, which is, we'll just think of these as like atomic symbols. We have a collection X, and these X are gonna be in subsets of some universe U. And so if you recall from like, say, the decision tree complexity, this notion of a query was important. And so it turns out that there's a very natural generalization of how we can do a query for things besides the hypercube. And so it's going to be just a subset Q, where this Q intersects each X in my domain, each element of my domain, in exactly one point. And where this in fancy Q is going to be the set of allowed queries for a particular domain. Okay, so let's just give some examples of how one would like encode combinatorics, or maybe not all of combinatorics, but just various familiar combinatorial domains as in like this framework. So for the hypercube, I think it should be somewhat straightforward. So for each bit string, I can record its index and its value, which is either going to be a 0 or 1. For permutations, we can take each permutation and do pretty much the same thing, where we have our indices 1 through n, and then the second coordinate's just going to be what pi maps that index to. And then we have the same, like, perfect matchings can be done in a similar way. And there are a lot more, and so there are other domains where this notion of where this encoding can be done in a fairly straightforward way, and I won't go through all of those. Okay, so here's like the main the main theorem of the paper. So this is it's that all these so. I haven't told you what most of these complexity measures are, and there's good reason for that. Take us quite some time, but what we're able to do is take all these complexity measures like degree, decision tree complexity, sensitivity. So we're able to come up with analogs of these for the set of K-sets, the symmetric group, perfect matchings, and some other natural domains. We're able to come up with analogs of those for these domains. Right, and so there's a few caveats here. So in that list of like objects that I thought were like, a part of combinatorics, those Q analogs we're not able to really recover in our framework, which is, so we tried really hard to be able to find some way of capturing, say, like K subspaces in this simplicial complex type framework. And it's not clear what to do. It would be, so this is actually one of the open questions we'll talk about at the end of the talk. But it's not clear how to approach the Q analogs. But anyways, so like I said, we haven't defined most of these, but I think sensitivity, we'll focus more on sensitivity because there's going to be more connections to algebraic combinatorics than some of these other complexity measures. So like things like certificate complexity and decision tree complexity. These have a more combinatorial flavor than sensitivity does. So remember, sensitivity was like this analytical thing. So right. So okay. So I guess I should pause here. So we're getting into the second part of the talk where we're coming up with analogs of these things for domains beyond the hypercube. So if we have any questions, now would be a good time to ask them. Okay, so we'll move on then. Right, so let's, like we did with the hypercube, let's start with degree. So let's decide what, so what should this degree complexity measure be in this more general framework? So we're going to say a polynomial is just a function on our domain X of the form as follows, where we have where our terms are indexed by these indicator functions. So here, this is an indicator function for whether X is contains S, and S, these are just going to be things of our universe. So or subsets of our universe, I should say. So so for example, if this was like a permutation, like if our domain was a permutation, and we could take S to be things like the symbol 1 maps to 1 or 2 maps to 2. And then the CS here, these are just coefficients for those indicator functions. And so, so I think this is a fairly natural notion of degree for these functions. And you'll notice that I'm calling these, we have spatial in parentheses over here. So there's a reason for that. So I'm calling this, so this is technically, let's call this the spatial degree of a polynomial. Okay, so the degree of a polynomial is just going to be the size of a largest S such that C sub S is not equal to 0. So sorry, I'm getting ahead of myself. So I didn't define what degree is yet, but now we have the proper definition. So, okay, so the degree of a Boolean function f, this is just going to be the least degree of a polynomial p such that f of x equals p of x for all x in our domain. So there's something to notice here. So like I can have multiple polynomials that define a particular function f. So this so it's not unique. So degree is just going to be the polynomial of least degree that such that I can represent my function f. Okay. So this is a spatial degree. Okay, so notice in the hypercube, we had this nice spectral notion of degree, and the spectral and the spatial notions of degree coincided. So this is a subtle point that I think is very important that I didn't really appreciate until I started working on these sorts of problems. But like, if we just take an arbitrary domain X, so this typically, it doesn't have something like an orthonormal basis of characters. So that was something that was very peculiar to abelian groups, in particular the hypercube. But one thing that it does have is a decomposition into irreducible representations. Okay, and so in particular, so in abelian groups, you can the characters are irreducible representations in that case, and so this is a so here we're generalizing this notion of a character to irreducible representations. Okay, so I'll just give some examples of this that we're probably all familiar with. So the Johnson scheme, and so here this notation R bracket, this R bracket notation means I'm just considering real valued functions over that particular domain. So this decomposes into these things called two-row spec modules. And these spec modules are irreducible representations of the symmetric group. Okay, and so the permutation scheme, we can decompose this into Sn cross Sn modules. And again, these S lambdas are the spec modules. And we can also do this for the perfect matching scheme. And so here, this 2 lambda means that I take a integer partition lambda and I double each part. So the partition 1, 1, 1 would actually be 2, 2, 2. Okay. So as I said before, this is going to be our notation for real valued functions on the domain. And now let's assume that we can identify our domain X with a coset of the symmetric group. Okay, so this is I'll say the right definition for spectral degree. And so what we're going to do here is we're going to look at our function, our real valued function, and we're going to consider its projections onto these isotypic subspaces. And we're simply going to consider, so we consider all these projections, and we're going to just take the max of lambda. So this bar lambda notation, this just means the number of cells in lambda as a Ferris diagram, and this lambda 1. So this lambda 1 is the first row of this Ferris diagram. So in other words, this so bar lambda minus lambda 1, this is just the number of cells below the first row of lambda. And so it turns out that this is actually the correct notion of spectral degree. And so we'll see why it's correct in just a moment. But right, so here's our definition of degree. And so what's not at all clear is, okay, so I have this definition of degree that's spatial. So this was involving these indicator functions. And I have this, this spectral degree. So why would they be equal? And so, I mean, this is something that doesn't require proof really on the hypercube, but it does require proof in other domains. And what's really cool, I think, and so maybe folks in this seminar group will appreciate this, is that this is sort of the bread and butter also of Erdos-Corrado combinatorics. In particular, a lot of these big results, and I shouldn't say big, so a lot of these nice results in Erdos-Corrado combinatorics tell us that the spatial degree and the spectral degree are in fact equal. And so these indicator functions that we were considering earlier, if you're Erdos-Corrado minded, you might have considered these to be just characteristic functions of these canonically k-intersecting families, where so we look at something like a set of size k, and we just consider all the elements in our domain that contain that set S. Right. So Karen and Chris came up with a canonical terminology for this. There's a lot of terms floating around in the literature. So these things are called canonically k-intersecting. And so kind of like one of the cool things that comes up when you're trying to prove Erdős-Colorado results is that you get that these canonically k-intersecting families, they span the space of these spectral degree k functions. And so this is, yeah, so this, I mean, maybe after the fact, it seems like a no-brainer, but like certainly when you're deriving these results, it's not clear. And so this is known for k-sets, and the seminal paper of Ellis, Friedgut, and Papel showed this. And you can also do it for, you can also show this for perfect matchings. And so the analogy here, to bring this back to the k-juntas that we were talking about earlier on the Boolean cube. So remember, these guys were just things that depended on just k coordinates of the hypercube. So these canonically k-intersecting families, they're the analog of k-juntas. So these are functions on my domain where their value only depends on whether or not it contains S or not. And so and S is just a subset of the universe, and in this universe. So we're just looking at sort of these elements of like these k elements of our universe to determine the output of the function. Okay, and so this is our picture for these other combinatorial domains where we have the symmetric group acting on them. So before we had our levels were indexed by sets. Now they're indexed by integer partitions. And we still have the same picture. We have the constant functions being low complexity, the parity functions being high complexity, and these degree k functions, these are just partitions where I have k cells underneath the first row. So this is the picture we should all have in mind for these functions that like this Fourier view of functions, real valued functions on these domains. Okay. So we should define what a decision tree is. So recall in our setup, our universe for hypercubes, we have the index followed by the value of the bit. And we have this, and our domain is just going to be, for each bit string, we encode it as such. And our queries were of the form, so remember that each query has to intersect each element of our domain in exactly one spot. So for instance, if I consider a bit string, it can't be the case that the ith coordinate is both 0 and 1. Rather, it just needs to be, it just has to have, has to be one of those two. Okay, and so this would be the decision tree setup. So, so I query x1, and if it's 0, then I query x3, etc. So now we're going to generalize this to permutations. So permutations, recall we had our universe was just these tuples where each one was drawn from an n-element set. And we had the index and where the permutation sent the index as our representation. And so now here are the queries. So it's a bit, it might be a bit hard to parse. So, but this would be the formal way of writing the allowed queries for permutations. So rather, it might be more instructive to just realize that our queries now, they're no longer of the form like is the ith index 0 or 1, but rather we're asking queries of the form, where does pi send the symbol I? Or which symbol does, so that would be something like this first query we have. So like, what does pi I equal? And so if it equals n, then we take this rightmost path here. And we can also ask queries, where does, what symbol maps to k? And so this would be the inverse. So let's see here. So it says my internet connection is unstable. Do I need to repeat anything?
No, it's been fine.
Yeah.
Okay, great. Thanks. Okay, great. So the queries we can ask now are of this form. So what's the, so we're looking at pi I and pi inverse. And so these are the questions we can ask. And again, we have this property that if these are our queries, then we can partition the space of permutations based on these queries. So for instance, in this example, we could look at, so like this rightmost path. So if I look at all permutations that send I to n, and all permutations such that n maps to k, and then assign all those permutations the value 1. So that's what this branch means here. And so what's interesting, so recalling back to our main result, is that what we're able to show is that if you have a function, a real valued function on permutations that has low degree, so you can take spatial or spectral, they're the same. If it has low Fourier degree, then I can find a shallow decision tree, which I think is also, I can find a shallow decision tree for computing this function, which is, again, I think quite interesting. Okay, so I'm gonna have to pick up the pace a little bit here. So, okay, so we've defined degree, we've defined decision tree complexity. So these all have very natural analogs to, like, say, the symmetric group and other domains that I've decided to exclude from this talk. But now let's do sensitivity. So the definition of sensitivity we give in the paper is a little bit more involved, but it's for this talk, it's safe to take the following as a definition. So I look at my input, so it's just like before, but now I'm going to consider disjoint transpositions. So I'm going to have these transpositions act on my input, and so the local sensitivity is just going to be the maximum number of disjoint transpositions, such that when I let a transposition act on my input x, the function value changes. Okay, and sensitivity is, again, we're just going to be taking the maximum over all of that. Okay, so I think this is a very natural generalization of sensitivity. I mean, so the way I've written it right now, you don't recover, say, the hypercube, but this definition makes more sense for, say, something like permutations or perfect matchings or domains where there's a natural action of the symmetric group on it. Okay, so one thing to notice is that, so these flip graphs, okay, so things like transposition graphs, these are things that that Sebi considered in his talk on the on coloring. So he considered the flip match of the perfect matching graph. So one thing to notice is that these, if you look at this graph where you have things that are connected if they differ by a transposition, they actually contain many large hypercubes as induced subgraphs. And that's going to be kind of the main observation here that we use for getting a sensitivity theorem on some of these domains, other than the hypercube. Okay, so the idea is that with this observation, we might be able to reduce things to the hypercube. Okay, so the goal here, just to be clear, so we've given a definition of sensitivity, and now what we want to give is some sort of analog of Huang's sensitivity theorem for these other domains like permutations or perfect matchings or things where we have this, say the symmetric group acting on them. Okay, so so this definition that I'm going to give is for the symmetric group, but in our paper we generalize it to a broader class of combinatorial objects. So we're calling this thing a pseudo-character. So a pseudo-character is just going to be a function on the symmetric group whose domain is 0 plus or minus 1. And the reason why we're calling such a function a pseudo-character is that it's reminiscent of the characters on the hypercube. And so, of course, the characters on the hypercube don't have a 0, but we'll see momentarily that these chi's are going to serve the place of characters, like serve the same role as characters did on the hypercube. Okay, so we say that a pseudo-character is 0-1D inducing if the support, excuse me, if the support of chi can be partitioned into subsets C sub I, each of size 2 to the D, and each of these is accompanied with a bijection. So from the hypercube of dimension D to Ci, and so it's going to satisfy these two natural but somewhat lengthy conditions to write down. So the idea, so we'll tackle one first. So the idea is that if I look at A and its neighbors, B1 through BD, then under this bijection, this is going to send, so this bijection that we have, phi sub I, is going to preserve, it's going to preserve the neighborhood structure, so to speak, with these flip graphs. So it's going to send neighbors to disjoint neighbors. And for 2, so we have, if A and B are neighbors, then whenever we have A and B and we apply the bijection phi sub I, this chi is going to behave like the parity character would. So this, so if any of these definitions, if it's unclear what's going on, we'll have an example on the next slide that clears things up. Okay, so yeah, so the idea is that we want chi to be, when we restrict chi to C sub I, we want that to be the parity character. And so this is one of the reasons why we call this a pseudo character. So this is one of these things where maybe I perhaps should have started with the example to motivate the definition. But here's what we mean by this. So let's just take permutations. So this 2, 3 here should actually be 3, 4. Sorry about that. Right. So here we define phi. And so phi is just, this is our bijection. So we're sending phi to the standard base. So 1, 2 goes to the first standard basis vector. 3, 4 goes to the second standard basis vector. 5, 6 goes to the third standard basis vector. And so here's a picture of it. And so these red points are going to evaluate to -1. And these black points are going to evaluate to 1. And so this bijection, if you look at, if you look at the neighbors here, so let's just take 1, 2, 3, 4. So if I look at 1, 2, 3, 4, and I subtract, and I do a set subtraction here, then I'm left with 3, 4. I do a set subtraction here, I'm left with 5, 6. And same thing here, I'm left with 1, 2. And these are all disjoint. So that's what's meant by this first condition. So this bijection preserves disjointness. Okay. So there's a reason why we're considering these characters. So these 0-1D inducing characters. So and the reason is as follows. So this is going to show us how we can reduce sensitivity on X, our domain X, in particular, let's say permutations. This is how we can reduce sensitivity on permutations to the case of the hypercube. So I'm going to take a Boolean function f, and I'm going to suppose that its inner product with this pseudo character that's 0-1D inducing is non-zero. Okay, so I probably haven't given us enough time to really digest the definition, but take my, so we have this fact that if it's 0-1D inducing, then we can write it as, remember, we can partition the support of chi into disjoint sets, these CIs. And the fact that it's not zero means that there exists an I such that I can just consider one of these terms. So this for CI. Okay, so now we're going to define a Boolean function on the hypercube with respect to this bijection that we had. So this I is the same I that is on the right-hand side in the equation above. So we have this Boolean function G. And because we have this non-zero inner product, and the fact that chi is really the parity character, and so recall the parity character is just corresponds to the set D, all the elements of D. So because of this inner product, we have that the degree of G is clearly D. And so now we're going to reduce to Huang's sensitivity theorem. So I have a Boolean function on the hypercube G, and so it's of degree D, and so I know that it has at least root D neighbors, such that if I evaluate G at the neighbor, then the function value changes. So here we're just reducing to Huang's sensitivity theorem, and because this bijection that I had was nice, that it took neighbors to disjoint neighbors, we have this following chain of inequalities. So what we've done is we've just reduced to the hypercube case. Okay, so it's not okay. So this is great, but I mean, we need to. There's some more details that need to be worked out. In particular, and we need to have a bunch of these 0-1D witnessing pseudo characters to witness all degrees of our domain. And so we say that a domain is witnessing if I take a degree D and I consider the space of functions that are of degree no greater than D, then this is spanned by pseudo characters. And every degree D pseudo character is we also require that these pseudo characters be 0-1D inducing for some D. And this D less than 1/2, don't worry about that for now. So the question is, all right, what should these XDs be then for the symmetric group? We've given this definition, we've shown that we can reduce to the hypercube, but this is all contingent on the existence of this nice collection of these so-called pseudo characters. So these things have to exist for them to be useful, of course. And so it turns out that so this is where the representation theory of the symmetric group becomes quite handy. So if you know a thing or two about the representation theory of the symmetric group, when you think of 0, ±1 valued functions on the symmetric group, that span the space of degree D functions on the symmetric group, then the first thing that comes to mind are these so-called standard polytabloids, which form a basis. So one can show that if you take XD to be the set of standard polytabloids, where we have no more than D cells below the first row, then this gives us the right collection of pseudo-characters to where we can conclude the following result. So we can conclude that the sensitivity of F is no more than the root of the degree of F divided by 2. And we can show a similar result for the perfect matching scheme. Okay, so the take-home message of that was that by using the representation theory of the symmetric group, in particular the existence of this nice basis that's called the polytabloid basis, we can reduce sensitivity on these domains to the hypercube, which is also really neat. Okay, so I'm out of time. So I had some applications, but I will skip over these, and I'll just leave you with a list of open questions that I think are. I'll leave you with a list of open questions that I think would be interesting to follow up on, and I think everything here should be self-contained. So I'll let you read that, and I will conclude the talk then.
Thanks, Nathan. Do we have any questions?
Yeah. So thanks for the talk. And you mentioned that you have proved something about the quantum query complexity. Yeah. How does that relate to your result?
How does it relate to what? Sorry.
What did you prove about the quantum query complexity in your theorem?
So we proved that quantum query complexity is polynomially related to these other complexity measures. So you can look at the paper, and to be honest, to tell you the exact relation that we proved, I would have to look at the paper again. But we wanted the main thing that we showed was that it belongs to this equivalence class of complexity measures where things are polynomially related, and also that quantum query complexity is still well defined in these domains. So
right. So you proved you cannot get very much of a speed up in some algorithms.
Sorry, can you repeat the question one more time?
Yeah.
I'm having trouble hearing you.
If those complexity classes are polynomially equivalent, so does it mean you cannot get very much of a quantum speed in some kind of algorithms?
Oh, so I don't think that's the case.
So just to answer your previous question, then there are these classical results relating all these measures in quantum query complexity for the cube, and we recovered them, but there are newer results which are better, and we don't recover them.
Thanks, Yuval.
Is there a nice way to say why the Grossman scheme doesn't admit like a simplicial complex description, or is it just that it doesn't, and you move on?
A nice reason. So I don't really have a good answer to that question. Maybe Yuval does, but so one thing that I tried really hard to do was to give so a lot of I didn't talk about it, but a lot of these some of these results have a connection to Robinson-Shinstead-Knuth correspondence, and in particular, so like for instance, with permutations, case sets, perfect matchings, multi-slices. So I didn't talk about the multi-slice, but that's another domain that's prominently featured in this paper. There's a connection with Robinson-Shinstead correspondence. So you can encode these things as like generalized permutations. And generalized permutations, so if you've seen RSK, then you'll know that some of the domains that we considered, you can think of them as being like generalized permutations in that regard. And I tried to come up with an RSK correspondence for Q analogs, and I just flat out couldn't do it. So it's, I think to answer your question, I think that there's just fundamental differences between the symmetric group and the general linear group, where morally you think that it should carry over nicely. There should be a Q analog when there just isn't. I don't know. That wasn't a very good answer.
No, but it's a fair answer. Like, it's not a very easy question.
Yeah. Yeah. Anyways.
I'm just curious, Nathan, are you, among these open questions, are you specifically interested in like particular ones? Are you working on some of these, or?
Yeah, so one thing that I'm interested in is, this classification of degree 1 Boolean functions on other domains. So I should mention that two of our audience members here, Yuval Filmus and Ferdinand Iringer, they have a joint paper where they classify some of these degree 1 Boolean functions on domains like the Grassmann scheme, other Q analogs, some more schemes that are finite geometrical in nature. And so I really like this program because like these degree 1 Boolean functions, I think of these as just being quite fundamental. I mean, they're fundamental to Erdős-Corrado combinatorics, for example, but also I just think it's good taste. Like, what are the, in combinatorics, we like Boolean functions because these are characteristic vectors of sets. And what are the degree 1 sets for that particular domain? I mean, it's a very clean question, and I like the math that comes up. So unfortunately, I wasn't able to discuss it too much, but we were able to, in this paper, we were able to slightly extend their classification to perfect matchings. And what's cool is that, to prove this result, notions like sensitivity that we defined we defined it for the symmetric group, but there's a way to define it for perfect matchings as well. And these notions, along with some polyhedral theory, can be used to classify the degree 1 Boolean functions on the perfect matching scheme. So in particular, they're these canonically intersecting families, namely like the characteristic vectors of all, the characteristic vectors of sets of perfect matchings that all contain some fixed edge. So like the edge 1, 2, the edge 3, 4, etc. But it also contains these triangles. So in particular, the characteristic vectors of perfect matchings that intersect a triangle of the complete graph in exactly one spot. So I have a triangle IJ, JK, KL, and I consider all the perfect matchings that intersect that triangle. And this is, and so the reason, so this is related to the odd set constraints actually of the perfect matching polytope. And so I thought that was cute. So I'm probably going on, going in too much detail here, but so you can take a peek at the paper if you want to see how the perfect matching polytope plays a role in this classification of degree 1 Boolean functions on the perfect matching scheme. But so to answer your question, I think 4 should be done for as many domains as possible. And I think 3 is interesting. I just don't have, I haven't worked on it that hard yet. And it could be that it's quite hard. Yeah, and I thought about one for a long time and I'm completely stumped. So maybe, I mean, we have Ferdinand in the audience who's a Mr. Q analog. So maybe, or at least a good finite geometer. So maybe he has some idea on how to do that. I won't put you on the spot though.
Yeah, I discussed that with Yuval a few 2 months or 1 month ago, quite in some detail. And yeah, what is, I mean, when you can look at all these complexity measures, it's tricky to define what you want to have from a Q analog was my takeaway from when I was thinking about it 2 months ago, I think.
Yeah.
Because you probably you have to say, when you have your polynomial relationships, what you will lose and so on.
Yeah.
Just a point number 3 is actually now working with Nathan, and we have an answer for some domains, like symmetric group. It's a classical answer for the slice, multi-slices, Grassmann scheme. Sorry, perfect matching scheme. Grassmann scheme is also classical.
Yeah.
Maybe I can add to Nathan's answer on point 4 a little bit more, if it's
sure.
Yeah.
I guess I should check with Sophia. I think we're 10 minutes over now. Is it okay?
I mean, if people want to leave, they can leave. It's fine.
Okay.
I mean, one reason why point 4 is interesting, I think, is also because it was investigated in various of these domains independently from very different directions. For example, degree 1 functions are often simply equitable partitions in distance regular graphs. They are often simply sets with dual degree 1. If you know the paper by Chris Gotzel, Bill Martin, I think Brauer and Kuhlen. And in finite geometry, they were investigated for the Grassmann scheme. There are tons of paper on Cameron-Lieber line classes, which are again the same concept. So this point 4 was rediscovered by many people in various different ways. I think that also shows it's a nice thing to do.
Yeah.
Nathan, if I may ask a question.
Sure.
Do you get a generalization of noise sensitivity in your framework?
That's a good question. So it turns out, and Yuval can help me out if I'm wrong here, but for noise sensitivity, I think the right analog here is it's not really what we have. So let me go ahead and just recall our definition of sensitivity. So I've underlined disjoint here. So for instance, so like it could be like 1, 2, 3, 4, but like not 1, 2, 2, 3. So these transpositions that we have, like they shouldn't overlap. And I think for the probability, for noise sensitivity, I think the right definition is that you want to just replace disjoint with just arbitrary transpositions. And so there are some results in noise sensitivity that consider this different definition where we're no longer requiring the transpositions to be disjoint. And this is, so in the paper we call this edge sensitivity, because this is where you're kind of thinking of the transposition graph, and so like that's replacing the hypercube, and you're looking at neighbors and you're asking which of my neighbors in the transposition graph has a different function value than I do. And so I think that's the right definition of sensitivity to get those sort of noise sensitivity results. It could be, yeah, it could be that there's a way of doing noise sensitivity in our scenario, but I haven't thought about that. But yeah.
I can add, then we know how to define noise sensitivity for all these domains. It's using the Laplacian. So you just need a graph, like the Johnson graph, Grassmann graph, whatever. So you have a Laplacian, and now you can define noise sensitivity in the obvious way, like exactly the same way you do in the cube. And there are lots of results about it. And actually, many of the results that Nathan quoted are about noise sensitivity. So they're about small set expansion, which is like roughly the same thing. And like Nathan said, for the Laplacian, then we don't have this distortions condition. So you can define sensitivity without this distortions condition. And we have an example showing that this is not polynomially equivalent to our definition.
That's right.
Is it possible to get a generalization of the Kahn-Kalai lineal sort of theorem?
Sort of. So you can get it for what's known as global functions or pseudo-random functions. So this is works by Noam Lifshitz et al. And lots of people. So it's false in general, like it's false for arbitrary functions because these domains tend not to be hypercontractive. But if your functions are global, which I'll define in a second, then it does work. So what's a global function? So if you look at the link, so you fix some of the inputs to the function, then it doesn't affect the expectation of the function by too much. Okay, so that's your Boolean function. Then if you say that x1 equals 1 and x2 equals 0, then the function still has roughly the same expectation. So a function is global if this condition happens for all small settings of parameters. And you can do the same about, let's say, symmetric group or whatever. And then if a function satisfies this condition, then you get like KKL. And if you look at the archive of the Noam Lifshitz, you'll find proofs.
Okay, thank you.
Thanks, Yuval.